Welcome back to this course. In this lecture, I will be continuing my discussion on the overview of different engineering material classes. However, before I do that, let me also show you how some of the materials are additively manufactured, and then I will be first showing you some videos so that you continue to appreciate the additive manufacturing processes, at the same time learn some of the key attributes of the material classes. So, this is first video. Now, let me go back to where I stopped in terms of my discussion on engineering materials is concerned. After showing you these 4 videos, let me revisit these key slides to remind you that engineering materials can be categorically classified into 3 primary material classes: metals and alloys, ceramics and glass, and polymers, each of having their own key advantages. Like metals and alloys have high toughness, modest hardness, and lower melting point. Ceramics and glasses have low toughness and strength variability. Polymers have high flexibility but low strength. So, if I want to show you this in one specific plots, just to show you what is the comparative advantages of 3 different material classes, then let me draw this plot. So, along x axis it is strain is plotted, along y axis it is stress is plotted. In engineering terms, stress is force by original cross sectional area. In engineering terms, strain is the change in length by original length. So, just for your reference, I am showing you typical dog bone type of geometry, which essentially follows the required ASTM guideline, and this dog bone type of geometry is pooled in tension. That means equal forces are being applied to opposite directions. It has a gauge length. Gauge length means the part of this test coupon samples with uniform cross section area. In case of ductile metals, it is linear. So, it is a straight line followed by non-linear part cross sign essentially means it fractures. In case of ceramics, it is brittle. Under tension, it has a lower strength. So it fractures with very low strain to fracture. So now if you consider the elastic modulus E for metals is Em, elastic modulus of ceramics it is C. So this is your metal, this is your ceramic behavior, and this is the thermoplastic polymers like polyethylene, ultramode polyethylene and so on. So I put a dotted bar. Dotted bar essentially means the scale is large and many times it can go to greater than 100% strain to failure, that is epsilon f. Now if you look at one parameter elastic modulus, that is the slope of the linear part of this stress strain response, you would agree with me that EC greater than EM greater than EP. What it means that elastic modulus of ceramics is much higher than metal, is much higher than the polymers. How about strength? So suppose this is the strength of metal sigma m, this is the strength of metal sigma c, and this is the yield strength kind of, this is kind of sigma p. So if you consider the sigma values, the strength, that's maximum load bearing capability, as I have mentioned in the last lecture. So sigma m greater than certainly sigma c, certainly greater than sigma p. So this is the maximum measure of the maximum load bearing capability. What is the strain to failure? Strain to failure is epsilon p is greater than strain to failure epsilon m is greater than strain to failure of ceramic C. So from this description in this particular slide, which is essentially describes tensile stress strain behavior or tensile deformation response of metal, ceramics and polymer, I am sure you will be with me to appreciate the three facts. Fact number one is elastic modulus of ceramics is higher than that of metals, is higher than that of polymers. Load bearing capability of metals in under tension is higher than that of ceramics, is much higher than that of polymers. Strain to failure of any thermoplastic polymer those who are from polymer background, they know that there is a two broad classification, one is thermoplastic, one is thermosetting. What are those that I will be going to explain when appropriate time comes. In case of thermoplastic polymer, the strain to failure or strain to fracture is much higher than that of metal and that of ceramics. So as I said in the beginning of the lecture on engineering materials overview, I mentioned that each of the material classes has their unique advantages, and now we are in a position to appreciate that statement by the fact that for metals strength is higher, for ceramics elastic modulus is higher, for polymers strain to failure is higher. These three properties are not comparable for all the three material classes. So each of the material class outperforms other material classes in terms of one individual property. Whether it is elastic modulus, ceramics is the best. In case of strength, tensile strength, metals is the best. In case of strain to failure, polymers is the best. So strain to failure means what is the maximum deformation that the material can sustain without failure, and that maximum deformation that the material can sustain without failure, I think their polymer outperforms. However, their strength is very low, that means that deformation is possible only at low load. Okay? Right. So, I think these things, I think it should be clear to all of you. So, in the earlier lecture I have also mentioned briefly about the metals and polymers. So, let me explain to you little bit more on ceramics. Now, ceramics, this is an important structural materials. It has excellent hardness and wear resistance, corrosion resistance. It has a good compressive strength. One of the things that I must mention, that compressive strength wise, ceramics compression, under compression is much higher than the tension. In fact, one can derive and show you that compression strength of ceramics is at least 8 times that of the tensile strength. So, in the last slide you have seen that the metals tensile strength is higher than that of the ceramics. So, let us take the example. Example is stainless steel. Their tensile strength, let us say 500 megapascal, some specific grade. So, if the tensile strength 500 megapascal, compressive strength is also around 500 megapascal. Let us say ceramics, it is like 250 megapascal tensile strength of alumina. Let us take another example, alumina. Now, as I said that compression strength of ceramics is 8 times higher than that of the tensile strength. What it means, for the polycrystalline alumina, compression strength is around 2 gigapascal, 2000 megapascal, while the tensile strength can be as low as 250 megapascal. So, again compression strength wise, ceramics are much better than that of the metals, because metals have, let us say, one of the classic materials is stainless steel, which has a compression strength can be as modest as 500 megapascal. So, this again places the importance that each material classes have their distinct advantages, and that as a material scientist, as an engineering scientist, it is our responsibility to exploit the advantageous properties of different material classes in the most thoughtful manner, right, to when you design engineering components. So, this in biomedical applications, many can be used for artificial joints and bearing components. Ceramics can be typically or traditionally they are classified as oxide ceramics and non-oxide ceramics. Oxide ceramics means alumina, zirconia. Non-oxide ceramics means all the carbides, nitride, borides and so on. Okay. These are non-oxide ceramics. Some of the popular examples of the ceramics for biomedical applications include hydroxyapatite, alumina. These are ceramics which are used for heart tissue replacement applications. These are commercially used as powders, as granules, hydroxyapatite I am talking about, and these are clinically used in human patients as in many regular surgeries. Alumina, Zirconia-toughened alumina is used as femoral ball heads in many orthopedic devices. So, what are the ceramics? This is a textbook type of definitions. It is a compound of metallic and non-metallic elements like I mentioned, right, alumina. Aluminium is metal, and then you have a oxygen in 2:3 ratio. So, alumina is different than aluminium metal. Aluminium is metal, alumina is its oxide form, that is ceramic. So, where the interatomic bonding, this is very important, can be either ionic or covalent bonding, like oxides or carbides. So, carbides examples is titanium carbide, zirconium carbides, and so on. Ceramics are well regarded for high compressive strength, I have mentioned, high temperature properties. I will come back to this point in the next few slides. Refractoriness, that is also a result of high temperature, ability to sustain high temperature without compromising on the structurally relevant properties. That is what is important for refractoriness, wear resistance properties. The key point is that engineering, broad spectrum engineering applications of ceramics often restricted by low fracture toughness. I remind you that fracture toughness is essentially a measure of crack growth resistance. So, ceramics is a low density material. So, this particular slide also shows you density of different metals, like iron or steel has a density around 7.8 gram per cc, copper is little high, more than 8, moly is kind of 10, and tungsten is as high as close to 20 gram per cc. Alumina as a ceramic, it has a density, that's model ceramic or classical ceramic density of 3.9 gram per cc. Iron has 7.8 gram per cc. What it means that density wise alumina is half of that of the steel. Therefore, if you take a component of equal volume of steel and alumina, alumina is lighter, almost like half of the weight that of the steel, that of the alumina component will have half of the weight that of the steel, is half of the as light as much lighter than that of the steel. Now, if you look at the polymers, many polymers like polyethylene, thermoplastic polymers and all, they have a density of 1 gram per cc. So, when you compare to that of the roughly 0.9, 0.8 and all, which you compare with that of the steel, it is like 1/8 of that of the steel. So, again if you take an engineering component of certain volume and then if you compare with a polymeric component of similar design, shape and also identical volume that of the steel counterpart, the polymeric component will weigh 1/8 time that of the steel. So, therefore, this example essentially shows you that how important is this density. It has also better hardness, ceramics and elastic modulus. Hardness wise, you can see that micro hardness, that some of the ceramics, cubic boron nitride, boron carbide, it has much higher hardness that of the tungsten, moly and some of the refractory materials. Elastic modulus wise, tungsten carbide has much higher elastic modulus. So, this places the importance that why these materials are sought after or why these materials are quite widely used for many engineering applications. This will be my last slide in this particular lecture. You have come across the term nanotechnology, and this nanotechnology, in nanotechnology the materials processing is done either by two approaches. One is that called top down approach, another one is called bottom up approach. So, these two approaches are quite judiciously used to make materials of different sizes and also different shapes also. So, nanomaterial is classically defined as the class of materials with sizes in at least one dimension in the range of 1 to 100 nanometer. If you look at the particles, all these particles should have diameter as 1 to 100 nanometer, then we call nanomaterial, or at least the majority fraction of the particle size So, if you plot the distribution and this is 100 nanometer, so majority of the particles should be in this 1 to 100 nanometer, then we call it nanoparticles. One dimensional nanomaterials, like you just see a alternate layer of the coatings. The coatings are oriented in different orientation, and if each layer of the coating or alternate layer of the coating, it has a thickness of 1 to 100 nanometer, then we call a nanostructured coating. The two dimensional materials here, if you see that individual grain size of these coatings can be of 1 to 100 nanometer, then we call it as a nanostructured materials. In three dimensional, any bulk materials where the individual grain, what is grain? Grain is the microstructural region where atoms are being placed along a specific planes, and this is called lattice orientations. And along these planes, these atoms are placed, and if you go from one grain to another grain, that along the lattice planes atoms are oriented differently. So, within a grain, lattice orientation is same. Across the grain, lattice orientation changes, and this particular area of misorientation is called grain boundary. Now, when you say it is a nanomaterial, what I am saying, at least one of the grains should have sizes in the range of 1 to 100 nanometer, then only you can call it a nanostructured material. So, these nanoparticles have been used for multiple applications, and these nanostructured materials are also used for many classical engineering applications. So, therefore, I thought this basic definition of 0 dimensional, 1 dimensional, 2 dimensional, 3 dimensional nanomaterials is important, and these nanostructured materials are also manufactured using the additive manufacturing technique. So, to recap, I have covered in this lecture the rest part of the engineering materials classes with a particular focus on how the three different material classes, metals, ceramics and polymers, they are different, and each of them have unique advantages in terms of the some properties, and here I have given examples of the mechanical properties for the elastic modulus, strength and strain to failure. I have also discussed on the one of the important material classes called ceramics, how they are different, how to define ceramics, what are the different examples of ceramics, and then how the ceramics have better properties than metals and polymers and so on. And at the same time, towards the end, I have also shown you examples of nanoparticles and nanomaterials. And at the beginning of this lecture, I have shown you 4 videos just to show you some examples of additive manufacturing, because this course is on additive manufacturing. Every now and then I wish to remind you about either the definitions of additive manufacturing or the different ways is additive, different ways or different machines that are used in the field of additive manufacturing to fabricate different classes of materials. But at the same time, this lecture and previous lecture essentially emphasize that what are the key attributes of the different material classes. Thank you, and I will come back to the next lecture with particular topic which is relevant to additive manufacturing. Thank you.